this video, I will be introducing you to Dalton's atomic theory. Dalton's atomic theory, in my opinion, is one of the two most important and paradigm-shifting scientific concepts ever devised. We are going to start off by asking a simple question. What is water made of from a very fundamental point of view? With limited information about the nature of the world, this is a difficult question. The consensus view in the Western world from the time of Aristotle to the Middle Ages was that there are four fundamental elements: earth, air, water, and fire. If water is considered to be a fundamental element, then it would be impossible to break it down further, and other substances would be devised from water combining with earth, air, and fire. This view was modified throughout the ages. For example, alchemists added silver and mercury as philosophical elements. However, it was not until the late Renaissance and early Enlightenment periods that natural philosophers realized this was an incorrect point of view. In the current day and age, we know that earth, air, water, and fire are not fundamental elements of nature. Furthermore, we take it for granted that water is made of atoms. However, we need to keep in mind that scientific knowledge is derived from what is known at the time and modified based on new insights. For atomic theory, these new insights were gained through experimental methods. If you think about it, it is actually remarkable that the atomic theory of matter was devised in the late 1700s and early 1800s, considering the huge level of accuracy needed to make that intellectual leap. The average lab of the late 1700s and early 1800s was more primitive than the average kitchen of the early 1900s. Measuring cups, the temperature control apparatus of coal ovens, and other equipment found in an early 1900s kitchen were all far more advanced than what these scientists had available to them. Nonetheless, they made a series of observations that still hold up today. Two important laws that we're going to discuss are the law of the conservation of mass and the law of multiple proportions, both of which were devised during this time. The law of conservation of mass states that in a chemical reaction, mass is always conserved upon conversion of the reactants, the chemicals that you start with, into the products, the compounds that you end with. For example, if we react 33.12 grams of lead nitrate with 11.68 grams of sodium chloride, we end up with 17 grams of sodium nitrate and 27.8 grams of lead chloride. In terms of the chemical equation, we say that our reactants, lead nitrate and sodium chloride, yield our products, lead chloride and sodium nitrate. In a chemical reaction, the plus sign on the reactant side means this chemical reacts with this chemical, and on the product side, that plus sign means and. So this chemical and this chemical. The arrow means yields. On the reactant side, we have 33.12 grams plus 11.68 grams. This equals 17 grams plus 27.8 grams, which equals 44.80 grams. Mass is conserved upon conversion of reactants to products. Another law is the law of multiple proportions. It states that if two elements, A and B, form different compounds, the ratio of the masses of A that combine with B will be different, but in each case, the ratios will reduce to multiples of small whole numbers. These two important laws led to the formulation of Dalton's atomic theory. Two other concepts are as follows. First, some substances could never be broken down into other substances. For example, gold could never be further broken down into a lesser substance. Another concept was that some substances could never be converted from one substance into another substance. For example, one could never convert lead into gold. We now know that this isn't completely true, and we modify this by saying that these acts can't be performed by chemical means. If you have a high enough energy source, you can break down these substances and you can convert one substance to another. In 1800, a natural philosopher, or what we would now call a scientist, named John Dalton, devised an atomic theory of matter, in which he formulated that all compounds are derived from atoms. I'm now going to take Dalton's atomic theory, as he originally devised it, and edit it to bring it up to date. Dalton's atomic theory had four main postulates. In the first postulate, he stated that all matter is made up of atoms, which are indivisible, indestructible, and cannot be changed from one atom into another. We now put in the phrase by chemical means at the end. His second postulate was stated as all atoms of a given element are identical in mass and properties to one another, but atoms of different elements have different masses and properties. We take out the mass in identical in mass and properties because we now know that isotopes exist. In his third postulate, he stated that compounds are formed by two or more different kinds of atoms, and that different combinations of atoms yield different compounds. In his fourth postulate, he stated that a chemical reaction is a rearrangement of different atoms. Using this theory, he was able to derive the structure of multiple different compounds, some of which are remarkably similar to what we now know. For example, he correctly identified carbon monoxide as one carbon and one oxygen, carbon dioxide as one carbon and two oxygens, nitrous oxide as one oxygen and two nitrogens, and sulfur trioxide as sulfur and three oxygens. He misidentified water as only containing one hydrogen, so instead of H2O, he called it OH. But considering the experimental apparatus, this is remarkably close. In summary, our key takeaways are mass is always conserved in a chemical reaction, atoms combine in whole number ratios to form chemical compounds, and that Dalton's atomic theory states that all matter is made up of atoms, all atoms of a given element are identical in properties to one another, compounds are formed by combinations of two or more different kinds of atoms, with different combinations yielding different compounds, and a chemical reaction is a rearrangement of different atoms. In the next video, I'm going to go through two examples of the law of multiple proportions. Just in case anyone wants to know a few fun facts about John Dalton, here are a couple. So first, he wasn't from the aristocracy. Instead, he was from what we would now call the middle class. This is unusual because in the late 1700s and early 1800s, most natural philosophers came from the aristocracy. Early in his career, he taught at both a grammar school and at a college. His students seem to have really liked him, but it's not known if that's because he was a good teacher or if it was from the fact that he was incredibly absent-minded and would therefore forget to punish kids for certain infractions they would commit. He got involved investigating nature because he was interested in weather. This led him to investigate gases, which then led him to investigate the nature of matter and develop his atomic theory. In addition, he was the first person to realize that there was a condition called colorblindness when he discovered that he was blue-yellow colorblind, and therefore he was the first person to describe that condition in the literature.